Before we introduce the main postulates that go into special relativity, one point of definition should be made straightforward first. And it's something that's going to be mentioned many times, and this is the concept of the reference frame. Specifically, the inertial reference frame. So in this case, I have drawn what looks like two coordinate systems, and the two reference frames are then labeled either by S or S prime. Idea is that everything in each reference frame is not moving relative to each other, not accelerating relative to each other. And what makes one reference frame different from another is that one of these frames is moving with respect to the other. So if I have frame S here, if I say this one is stationary, then somebody in reference frame S looks at something in reference frame S prime and says it has some velocity v relative to it. So, for example, let's suppose that one of those reference frames is simply just me standing here at the ground, and the other reference frame is some sort of car moving away from me with some velocity v. If I had some sort of box here sitting on the ground with me so it's not moving relative to me, I would say that that box is in the same reference frame as I am. They are both in reference frame S. On the other hand, the car is moving both relative to me or relative to the box, and so this box is not in the same reference frame S prime as the car. Of course, I could have some sort of item inside the car, some piece of luggage in there. If I did that, well, that block inside the car is again moving away from me, so it's not in the same reference frame as I am. But that block is in the same reference frame as the car because relative to each other, that block and the car are not moving with respect to each other. So this is the basic idea of the reference frame. All the things collected together that aren't moving relative to each other, they all have the same relative velocity together. Also, this is a case without acceleration. That's what makes it an inertial reference frame. So with that point of definition of reference frames, here is the idea that goes into special relativity. There are really just two postulates. One is that the physics in any reference frame is the same as any other. The laws of conservation of energy and momentum, for example, are just as true in reference frame S as it is in reference frame S prime. Just because you have some sort of velocity doesn't mean you're going to be changing the way you do your experiments and what sort of outcomes you're going to have. That seems somewhat basic, but it's a point to say there aren't any special reference frames. All are equally just as good. As for postulate number 2, is that the speed of light is the same in all reference frames. And it's postulate 2 here that's really the one that's going to produce all the interesting things popping out that you've learned about with special relativity or going to learn, whether it's time dilation, spatial contraction, all those sorts of weird things. And this postulate should initially seem very strange to you. The idea that if I go from one reference frame to another, I would still measure the speed of light to be the same. So I need to highlight why this should be seen as weird. So let's take the example that I'm standing on some sort of moving platform. We could talk about the platform itself having a certain velocity v, and that velocity would be relative to the ground. So we're saying the ground is stationary and this train is moving along with some velocity v. I'm on top of the train. And normally if I throw a baseball, I'd be able to throw it with some other sort of velocity. Let's call it velocity prime just to distinguish it. So suppose I have a pretty good pitching arm and I can normally throw the baseball at 90 miles per hour. So we'll say v prime is what I normally throw the baseball at 90 miles per hour. And conversely, let's say that that train is moving along at a nice pace of 30 miles per hour. Well, if you wanted to say, all right, what is the relative speed of the ball to the ground? Well, you would think that the new speed I'd have, let's call that just u, just to have something that's a little bit different than v and v prime. You would think that the velocity of that ball would simply just be the addition of those two velocities. the velocity the ball normally has, and then the velocity of the train. Because in this case, v prime, the speed I normally throw the ball at, that would be the speed relative to me. I have speed to the ground relative of just regular v here, so you would think just normally it's a simple sort of addition. And this is what you would do normally with Galilean relativity, nice and straightforward. And this is then what Einstein is throwing out in the special case of light. So in this case, let's suppose again we have this train moving along with some velocity v. And in this case of me, instead of throwing baseballs, I have some sort of flashlight, and it can shoot off light in the forward direction. Now, normally, I would measure that velocity v prime as the speed of light c. That's what I would measure normally. Now, if somebody were here standing on the ground, and they had some sort of measuring device of the speed of light, again, if you were thinking normally, you would think that the speed that that person would get as the speed of light would be the normal speed, c here, plus the speed of that car, or this train, whatever moving object is pushing the light along. That's what you would normally expect. But Einstein is saying, no, this person here is still going to measure the speed of light as what it would be if this person here were just completely stationary. That is the weird thing. And it wouldn't matter if this train is moving at 10 miles per hour, 10% the speed of light, 99% the speed of light. No matter what, this person is going to measure the same thing. And this person here on the train, if you are able to measure the speed coming off from there, would be the same. Anybody else having to zip along in either direction, up and down, no matter what, they are going to be measuring the speed of light shooting off as the same. So that's why this postulate seems initially strange. Now, of course, you might have to wonder, well, why would anyone propose this sort of thing that seems so counterintuitive, goes against how we normally add velocities together? Why should we even expect this sort of effect? Well, often it's mentioned that there was the Michelson-Morley experiment that failed to find that there was any effect of ether drag when we were doing experiments on the Earth as the Earth spins around the Sun. Now, the experiment they had couldn't detect light speed changes very, very sensitively. There was some level of error that could have accounted possibly for things. So when they did their experiment, they didn't say they saw no effect. It was that their equipment couldn't pick up the effect. So that's not a definitive experiment. On a theoretical point, though, you might want to look, say, at Maxwell's equations. What was seen there is that when you apply the laws of electromagnetism, the light pops out as a wave, and you found that the speed of light popping out was based on the permeability and permittivity of space. Those sorts of things came out. But none of the work actually had any sort of assumptions about reference frame. So one of the natural things you might assume from that is, well, that's the speed of light you measure no matter what when it's in vacuum. So that could give some level of inspiration. And more importantly, once we actually take this postulate and apply it, we can actually then explain some of the things that were being used to trying to explain the failures of the Michelson-Morley experiment and other experiments at the turn of the century, and try to affect what they were doing, but without having to apply the ideas of some sort of luminous ether anymore. What effects happen is for the next video.